two things govern what we know about magnetism. Everything else follows from these two things. First is that the contribution to the magnetic field at a point, and actually two things are here and here, these are both the same. Let's back up. Okay, so what we have here is a contribution to the magnetic field at a point due to a charge moving with velocity v and a charge q moving with velocity v at a point is equal to this expression. It's a cross product of qv with the r vector divided by its magnitude divided by r squared, where the r vector is the vector from the position of the charge to the position at which you're calculating the magnetic field. And the equivalent statement is that the contribution is equal to this product. Now we have the proportionality constant K prime in both of them. And you could write that as mu naught over 4K if you wish. I prefer to write it without all the pi's, and to remember that mu naught is 4 pi times K. Okay, well, and you can remember that any way you want. You can put mu naught over 4 pi there if you like. And that's equal to the cross product of I delta L cross the r vector divided by its magnitude divided by the square of the magnitude of the r vector, where delta L is a current segment, a short, straight current segment, and r is the vector from that current segment to the point at which you're measuring the field, I being the current through that segment. I recommend that you understand as deeply as you can why it is that QV is equivalent to I delta L. You have all the information, all the tools you need to do that from various sources. Okay, and mostly from the introductory problem section. The other thing is, okay, so this tells you that moving charges, whether individual moving charges or charges moving in a conductor, create a magnetic field, just according to these laws. Then you have the fact that the force exerted on a charge Q moving at velocity v in the presence of a magnetic field B is just QV cross B. And since QV is equivalent to I delta L, you have this for a small segment carrying current. Now, if you have bigger segments carrying currents or distributions of charges moving at various velocities, you end up having to often typically do integrals to figure out the total contribution of all the little delta B's. Okay, and to be really rigorous about this, I should write that as dB and dl, the infinitesimal, and dl down here. Okay, well, let's see what some of the consequences of this law are. If we have a current coming out of the blackboard, that's indicated by this little bullseye type thing here, then according to this law, or let's take this one because we're talking about a current, the cross product of two vectors has to be perpendicular to both of the vectors. So any cross product involving I delta L is going to have to be perpendicular to I delta L. Well, whether I is going this way or this way, if the current is if the conductor is perpendicular to the blackboard, it turns out then that the magnetic field is going to have to be in the plane of the blackboard. Now, in the case where your current is moving out this way, well, let's figure that out. At this point, the R vector, as I say, goes from the point on the current segment, and let's take that to be this point here. The R vector goes from that point to the point at which you're calculating the field. So it's from here to here. So the right-hand rule, and I'm in the wrong position to use my right hand here. The right hand rule says, here's the direction of your current, and if you turn your fingers this way so that you're turning the current vector toward the R vector, your thumb moves this way. Your thumb points this way, and that's the direction of the magnetic field at this point. If the current was into the blackboard, then we'd have to be doing something like this, and the magnetic field would be going this way. Now, R is a radial vector for this circle that I've sketched. B has to be perpendicular to R for the same reason it's perpendicular to the delta L, because you're doing the cross product of the delta L vector with the R vector. And then you've got some constants that don't change the direction of that vector, or at least don't change the line along which the vector has to act. Okay, well that means if this is radial and this has got to be perpendicular to the radial, that it's tangent to this circle. So all around this circle, you can draw magnetic field vectors that are tangent to the circle. The circle is always at the same distance from the current segment, so the magnetic field vector is always going to have the same magnitude. So what I'm saying here, I know what I've written down, just the current's out of the board, so B is in the plane of the board. B is perpendicular to R, so B is in the plane of the board, and also perpendicular to the R vector, which is drawn in the plane of the board. So that the B vector is perpendicular to the radial vector, R being the radial vector for this circle, and I haven't, written down a lot of qualifying information, so we got to say, the radial vector to whatever circle the point lies on, at whatever circle centered at the current segment. Okay. Well, since B is perpendicular to the radial vector, it's tangent to the circle centered at the wire. The magnitude of the B vector, or the contribution, the delta B contribution, is just what? In this case, in this particular case, where the wire is perpendicular to the vector R, because we could, of course, figure the current at some point outside the board due to a segment that's in the plane, that's centered in the board. So not everything would be as perpendicular as we say it is, and I don't want to go into a lot of detail on that because we're just trying to do an overview here. The point is that with the system as I've described it here, the R vector is perpendicular to the delta L. The R vector divided by its magnitude is a unit vector. So the magnitude of L cross this unit vector is just equal to the magnitude of L. So we just have the magnitude of L, I, K prime, and R squared. And that gives us the magnitude of delta B. Okay. Now, just to be clear, I didn't really sketch it this way, and I might have been a little vague both here and in class. If we turn this around and look at it this way, we're just talking about a short segment that's in, or at least that crosses the plane of the board. So if this dotted line is the plane of the board, looked at from the side, our delta L segment is here along a wire perpendicular to the board. And I don't think I was very explicit about that. And so if you had some questions regarding that, that should help clear it up. Okay. If we have a long wire, and this is an attempt to sketch a dotted line or a dotted ellipse that represents a circle cutting the line at a perpendicular. with the center of the circle at this point, and your delta L increment here. Well, you have other delta L increments along this line, don't you? So if you want to get the total magnetic field at a point, well, this is just, and I called this B, got to call this delta B. This is just a contribution delta B of the magnetic field due to this one delta L segment. Okay, and we consider a segment to be, pretty much infinitesimal, pretty much almost zero length. So we get very little magnetic field, but that's how it's going to be oriented. Okay, well, if we divide this wire up into intervals, our delta L increment is just one interval. Now, the intervals on the right, if you work through the right-hand rule, are going to give you R vectors that aren't in the plane perpendicular to I, so that the B vectors are going to come out of that plane. They might come out a little bit this way, or go in a little bit that way, or even quite a bit, depending on how far away you are. Also, the delta B's are probably going to get smaller because your R is going to get bigger, and you're dividing by R squared. So you have a whole bundle, so to speak, of delta B's from all of these intervals. Now, the one thing that happens to that bundle is any delta B you get from an interval over here, if you have, let's say, equal intervals and the center is right in the middle of this interval, is going to be, in a sense, balanced by what you have over here. Both are going to give you delta B's in the direction perpendicular to this circle, or the direction tangent to this circle, in the plane perpendicular to the wire. But some of them are going to give you delta B's that are smaller than this, but that out of the plane this way. But on the other side, you have increments give you delta B's that are out of the plane this way. You're going to get a bundle of delta B's, and all the components in this direction, if you have a long wire, all the components in this direction are going to balance all the components in that direction. And you're still going to end up with the delta B, with a magnetic field B perpendicular to the wire. Now, that's kind of a hand-waving explanation, but if you've been through the integrals, for example, calculating the electric field of a uniform disk, uniformly charged disk, or even maybe non-uniformly charged disk, as long as the charge is symmetric about the line through the center of the disk, then at any point on the axis of the disk, if you have a positive charge, you're going to get an electric field in this direction. Okay, now if you move around the disk, all the contributions are like, they kind of make a cone around the disk, but because of the symmetry of that situation, all the components perpendicular to the axis cancel out. Now, you should know what I'm talking about. I'm not trying to describe it from first principles. This is one of the developments that you will have confronted in the text. The argument here is, in a lot of ways, similar to that one, so I kind of leave it to you to mess around with your right hand and with this situation. And then there's some implications of this that lead us toward Ampere's law, which does follow from this, but it's also an empirical law that's been well established.